So thanks so much, Stephen, for inviting me here. And it really is a joy because I did wander around here. And maybe you guys already know this, but this is hallowed ground for physicists for a whole bunch of reasons. But for me, the kind of primary reason, and I just have to share this with you, is starting in 1968, there was a series of experiments that were done here that were called the deep inelastic scattering experiments. And those were the first conclusive proof that a proton, which we had normally thought of as a point particle, a proton is actually a big bag with 3 quarks rattling around it. And that's same thing is true of a neutron as well. So dramatic physics. But this guy here, Richard Feynman, American theoretical physicist, he was part of the understanding of this behavior. Very smart guy. And in fact, I actually got to see him talk in 1982, and it would have been this auditorium had this auditorium existed then. It was actually a much more humble, modest version of this auditorium, somewhere within 100 yards of here, and that's been torn down now. But Feynman, in addition to thinking about problems like confinement of quarks, he was thinking about another problem at the same time that kind of lays on the boundary of physics and computation. And that's kind of why I date this field to 1982. This is a screenshot from a paper that he published in 1982. And Feynman had made kind of it's a simple observation, but it's sort of dramatic for its implications. Feynman observed that when you take quantum mechanical systems and you simulate them on computers, they run very, very slowly. So slowly that all but really the smallest quantum systems that you might care about are beyond the reach of computation. And I actually saw this firsthand because when I was doing my thesis work here, I was simulating fermions moving around 2-dimensional lattices, and it was painful. I was writing Fortran on an IBM mainframe, a 3081. So Feynman is a very smart guy. He looked at this problem and he turned it around and he saw an opportunity instead of a problem. He said, nature somehow is able to effortlessly move quarks and electrons and other particles. Nature can move them around effortlessly. But our classical computers, and now I think of them as classical computers, they have a very, very hard time with these simulations. So maybe we're using the wrong building blocks when we build computers. Maybe we should use the same building blocks that nature is using. And so hence was kind of born one of the seeds of this field of quantum computing. So I'll read a couple of words from Feynman's paper from 1982. He says, it does seem to be true that all the various field theories have the same kind of behavior and can be simulated in every way apparently with little lattice works of spins and other things. So when Feynman says various field theories, he's talking about quantum mechanical systems whose behavior we want to understand. And when he says little lattice works of spins and other things, he's describing what today we would call a quantum computer. So Feynman was not the only person thinking about these ideas at that point. There were a bunch of other physicists. Charles Bennett was thinking about the reversibility of computation. Paul Benioff, a physicist at Argonne National Labs, was thinking about a Turing machine, our model of classical computation, and could you build a quantum Turing machine? David Deutsch, a physicist from Oxford, was trying to figure out how to program a quantum Turing machine. And so by around the 1990s, early 1990s, this new kind of quantum computer and this new building block had sort of crystallized to some extent in people's heads. And the idea was we're now going to build or think about building a computer out of not bits but quantum bits or qubits. So a reasonable question is, well, what is a qubit? Is a qubit, an atom that's spinning this way, or just what is a qubit? And it's kind of a trick question in a way, because a qubit is not really a name for a physical system. A qubit is the name for a mathematical model of a physical system. And so in the quantum world, the reason that we talk about quantum mechanics is because energy in quantum systems appears in discrete possibilities. So if you look at a quantum system, one of the simplest questions you can ask about it is, how many energy levels does it have? And so it turns out that the simplest interesting answer to that question is 2. right? Because if a quantum system only has one energy level, it's too simple to even really think about. But lots of quantum systems have many or an infinite number of energy levels, so they're too complicated. But 2 is kind of like the simplest number that's non-trivial. So a qubit really doesn't refer to an atom or any particular thing. A qubit just means I've got a 2-level quantum system here. And so there's lots of different ways that you can build qubits. The company that I work for, dWave, builds qubits out of superconducting circuits. It's kind of interesting. The technology behind superconducting circuits is older than a lot of people realize. The concept of superconductivity has been known for more than a century. This guy Annealing observed it in lead, and he got a Nobel Prize in 1913. When you build circuits that are superconducting, just like with classical circuits that you could put resistors and capacitors and inductors into, when you build a superconducting circuit, there's this new circuit element that you can put in there, which is called a Josephson junction. And this guy, Brian Josephson, discovered that in the mid-60s. He got a Nobel Prize in '73 for it. So superconducting circuits have been around for actually quite a long time, but that's not the only option that you're forced to choose. You could trap some ions. There's a company in Maryland by the name of IonQ that's pursuing that approach. Microsoft is very hot on the notion of topological matter, very advanced. So there are lots of ways that you can build a qubit. So once you've built a qubit, how do you actually assemble a bunch of qubits into a working quantum computer? What is the architecture of that thing? So by around the early 90s, again, this notion of a sort of a gate model or circuit model quantum computer had sort of emerged as the right way to think about this problem. And so what I'm showing you here is what's called a circuit diagram for a little quantum circuit. Now, this is not like a circuit diagram for a classical computer. A circuit diagram for a classical circuit, you just put it on a chip and that'd be the end of it. You'd use it over and over and over again. This circuit diagram has time going from left to right. And each one of the horizontal lines that you see in there represents a qubit. So if you count, there are 9 horizontal lines, 9 qubits here. And so as time goes from beginning to end, you'll see there are these gates, these vertical lines that sit down on top of 1 or 2 or 3 qubit lines. And so each one of those gates actually can be represented as a mathematical operation. So the state of this 9-qubit system, you would actually write it down as a vector of complex numbers. And the fact that we've got 9 qubits means this vector has 2 to the 9th entries in it, 512 entries. And each one of these gates that you encounter is actually representing a matrix vector multiply. And that matrix is 512 by 512 times a 512 component column vector. So we've got a bunch of these matrix vector multiplies, and at the end we have some other vector. We project it onto a subspace, and that's what we get for our answer. So this is the standard model of quantum computing. It's a very abstract thing. It's sort of frankly, it's extremely difficult to develop intuition for this, but this is kind of, by around 1992, 3, 4, it was understood that this is really what you can get if you build computers out of qubits. But then the real question is, okay, Feynman had intuition that this would be more powerful than our digital computers. Is that really true? We need a nice example. And Peter Shor, a mathematician at Bell Labs, provided a great affirmative answer to that question. Peter Shor took a problem which is known to be very hard on classical computers, factoring. In fact, it's one of these trapdoor functions. It's easy to multiply numbers, it's very hard to factor, and all of modern crypto, well, a lot of modern crypto is based on that trapdoor property. Peter Shor showed that with a quantum computer, one of these idealized gate model quantum computers, you can factor. He combined a little number theory with some quantum Fourier transforms, and in fact, a quantum Fourier transform is nothing more than a regular Fourier transform or a fast Fourier transform. If you've ever done any numerical programming, you may recognize that phrase, the FFT. It turns out quantum computers of this form are very, very good at FFTs. So if you put them together, you can factor. And that little matrix you see there, this is a 3-qubit factorization circuit. And that matrix is an 8 by 8 matrix because 8 is 2 to the third, and all the numbers in that matrix are 8th roots of unity raised to various powers. So, wow, this is great. This is an exciting breakthrough. Yes, if we can build these quantum computers, they're going to be very powerful. But we have a problem. Noise and waves. So the reason I like this picture is because you can see waves. There are like 4 big waves coming into the shore. And waves are, well-known phenomena. Physicists think about them all the time. Waves can interfere with each other. And when they interfere, they can reinforce each other, constructive interference, or if they're out of phase, they can interfere destructively. But the key thing about that interference behavior is that it relies on the waves not being interfered with by something else. And something else would be noise. So in addition to these big coherent waves, you also have a lot of froth. And all that white stuff you see there, the little ripples on the surface of the water. So it's very easy to imagine that if this noise were turned up and up and up, then the incoherent behavior of the noise would overwhelm the coherent waves, and you would lose all these wonderful coherent interference properties of the waves that you're relying on. Well, it turns out that coherent wave interference is exactly what you're relying on when you take a matrix and you multiply it by a vector, because the elements in that matrix are combining different elements in the vector, either coherently or, constructively or destructively, depending upon the signs in the matrix elements. So if you've got noise in your quantum computer, it's going to defeat this coherent wave activity and you're going to lose your computation. So can you fix this? Can you deal with this issue? Classical computing provides some hope that the answer is going to be yes, because we know that people think about error correction in the classical world. If a cosmic ray hits your memory chip and it flips a bit, what are you going to do? Well, a lot of people have heard this acronym SECDED, Single Error Correct, Double Error Detect. So the idea is if I have a 32-bit or a 64-bit word, I can put a few bits on the side of the word, and those extra few bits are going to give me enough redundancy so that if one of the bits in my word gets accidentally flipped, my SECDED bits will tell me, oh, you've had a single bit error and it's in bit 17. So I can go fix it. And in fact, the DED part, double error detect, says you might have a double bit error, but I don't have enough power to tell you where it is. But at least you know that you've got the error. So the fact that you can do this classically holds out the hope, or held out the hope, that you could also do this quantumly. And sure enough, it turns out that you can error correct these quantum systems, which is crucial, because if you build one of these quantum systems, qubits in nature, nature's got noise. Noise is everywhere, and if you don't have a way of beating down the noise, then you're going to lose your quantum computation. So it turns out that you can do it, and there are a couple of names up here associated with the original ideas, but there's some bad news. The bad news is that the error or the overhead associated with correcting these quantum errors is much, much bigger than in the classical world. So as a data point here, I've looked at some analysis by some authors. O'Gorman looked at 1,000-bit Shor. If you could do 1,000-bit Shor, it would change the world, right? But in order to do that, which might only take about 1,000 logical qubits, error-free qubits, you might actually need to build more than 100 million physical qubits in order to correct that error. So the ratio, the amount of overhead required to combat noise here is actually tremendous in the quantum world. And this is actually one of the big barriers that the gate model people are they're trying to overcome right now. So that's kind of the end of chapter 1. Chapter 2 starts in about 1998 with a series of suggestions from different groups all over the world. You know how it's rare that just one person has a great idea. Usually a number of people have different versions of that great idea at roughly the same time. So Nishimori in Japan, Gabe Apley at Bell Labs, Seth Lloyd at MIT proposed a different model of quantum computing. It's different from that gate model that I showed you. And this model is referred to as annealing. So what does annealing mean? Well, actually, annealing is something that we're very familiar with. When you take a piece of iron and you put it in the fire and you heat it up and you bang on it and bend it and work it and do that over and over again, that's annealing using thermal energy. And what's going on there is this piece of metal has all these little domains in it, and these little domains are kind of aligned internally, but the domains are not aligned with one another. So you can think of the configuration space of this chunk of metal as being the orientations of all those domains. And if you can get all those domains to line up, then you get improved structural properties. And you can do that using thermal annealing. Nishimori suggested maybe you could do that same thing except using quantum mechanical annealing, not thermal annealing. So rather than heat up and cool down a sample, what we're going to do is we're going to sort of turn up the quantum fluctuations in the sample and allow those quantum fluctuations so that these little domains kind of figure out what's a low energy configuration, and then they can settle into a low energy configuration, and that's goodness. So in fact, the simple picture that comes out of this is a landscape. So this landscape represents some kind of, think of it as some sort of an optimization problem that we want to solve. And finding the low points in this landscape is actually, that is the computation that we're trying to accomplish. It turns out, even though this is a funny way to think about computation, it turns out that almost anything that we can do can be cast into the form of an optimization problem on a landscape like this. So a simple example is, suppose I want to add two numbers, x plus y, and get the result z. Okay? Well, I can just reorganize that equation. I can turn it into x plus y minus z equals 0. And then I can take that x plus y minus z and I can square it. Now, it turns out that if you do that, you end up with a little quadratic function of x, y, and z. And if that quadratic function is equal to 0, then x, y, and z satisfy the addition constraint. But if that function is non-zero, it's going to be positive because I squared that thing. And if it's non-zero, then that means that I have not satisfied the addition constraint. So that's a trivial example of how I can take addition and turn it into a landscape just like this, although that landscape would have 3 dimensions, and then the height would be sort of sticking out in the 4th dimension. This picture here has 2 dimensions, latitude and longitude, and a height above each latitude-longitude point. So I guess I should say one other thing about the difference between classical and quantum here. If I give you this problem and you've got a classical computer and you want to solve this, the natural thing to do is just pick a random starting point and you say, okay, here I am. Now I'm going to look at what happens to my height if I go north, east, south, west, and I decide that northwest is the most downhill direction. So I go northwest and then I do it again. So that's just gradient descent, right? We all know about gradient descent. And that'll get me to a minimum, although the problem is the minimum may well be a local minima. It may not be the global one. But you can combat that. You can actually simulate the effects of thermal energy. So there's a well-known algorithm, simulated annealing. And with simulated annealing, you generally go downhill. But using a random number generator, you allow yourself occasionally to go up. And if you're very careful with the way that you allow yourself to go up, and you take long enough time, you can convince yourself that you'll land in a global minima here. But the essence of this is that it's a 1 point at a time algorithm. The algorithm is typically only sensitive to the neighborhood of where you're standing at any point. With quantum annealing, the approach is completely different. We're going to use qubits to actually parameterize where we are in the landscape. And since I'm sure you've heard this phrase, qubits can be 0, they can be 1, and they can be both at the same time. So if you take that idea and apply it to this landscape here, what it really means is that I can actually prepare my system so that it's not at 1 point on the landscape. My system actually is like it's in a fog which is spread over the entire landscape. So with quantum annealing, the cycle that we actually go through is we start in this fog-like state, spread over the entire landscape, and at the same time we actually turn the mountains and valleys down, so the landscape starts off being flat. And then we go through this annealing cycle, which is typically quick. It might be like 20 microseconds. And as we go through this cycle, the fog condenses down to a point, and at the same time, we turn up the mountains and the valleys. So as the fog condenses down to a point, it sort of responds to this emerging landscape. It slides downhill, and by the time the fog condenses down to a point, it's sitting in one of these minima. Okay? So for me, that's actually a much more intuitive picture than the mathematical model of gate model quantum computing, where it's this cascaded series of matrix vector multiplies. So this is kind of how quantum annealing works. And if you want to take this metaphor more seriously, I should point out that our landscape is not really two-dimensional like this. Our landscape really consists of the vertices of a hypercube, and the number of dimensions in that hypercube is equal to the number of qubits we have. So it's not a continuous landscape, it's a discrete one. So dWave was born in 1999. We've been around for 20 years. And for the first 5 years of our life, we were actually not focused on building a quantum computer. The idea was to collect intellectual property around quantum and then use that to just sort of facilitate the commercial sector that was related to quantum. And that phase of the company lasted until around 2004. And then in 2004, something changed. This was before I was at the company, so I don't really know the internal dynamics, but something changed, and the company decided, yes, we do want to build a quantum computer. But an interesting thing happened, which is, I don't think, really widely appreciated. It was not the case that our company decided we're going to build an annealing machine because we like annealing. What we did actually is perform this technology-agnostic evaluation. We kind of went into this saying, well, we can build anything we want. Let's build the most sensible thing out there. And so we looked at the different physical device technologies for implementing qubits. Do we want to build superconducting circuits, trapped ions, topological matter, photons? What do we want to use for the physical substrate? And what's the architecture? Gate model, annealing, are there other architectures out there that make more sense? So we kind of looked at all these options, and we decided that the right thing to do is to build an annealing machine and to build it out of superconducting circuits. And this was a very pragmatic decision. It was a function of saying, we want to build something that works, that's scalable, given the technology available today. So what's the right choice? So this was a judgment call. And you can actually see here on the left side of the slide that can is the outer layer of cryogenic containment device. And if you take that can off, there's other cans inside it. If you take them all off, you end up with that assembly that you see here in the middle. Those are temperatures, so our system actually runs at a little bit lower than 20 millikelvin. Deep space, for reference, is about 200 times warmer than our system is. And so the processor, which lives down here, that's the processor chip. If you've happened to seen one of the pictures of our system, it's a big black box. It's about 3 meters by 3 meters by 3 meters. That whole system there is just to create the environment for that one chip over there. So we started down this path in 2004, and it's worth pointing out that it took us 7 years to get to the point where we had a product that we felt like we could deliver to somebody, which is a useful number to keep in mind when you look at other companies that have just gotten into this game recently. So in 2011, we introduced the dWave 1, 128 qubits, 352 couplers. And these couplers, I'll show you exactly what they turn into in just a minute. They turn into quadratic coefficients in an objective function, and we're going to use those quadratic coefficients to create that landscape. So that was the dWave 1, and the little pattern that you see there is actually, it represents the layout of the qubits on the chip itself, which turns out to be kind of important if you actually want to take a logical problem that came from the wild and then embed it into our chip. More on that later. I joined dWave right here, 2012, and then second product generation. This was Lockheed, which was our first customer, upgraded to the second generation. And this was the point in time where the Google-NASA collaboration purchased their system. So at this point in time, we actually have two physical systems now installed in California, one in Southern California down at USC, owned by Lockheed, and then the second system is quite close by here. It's down in San Jose at NASA. NASA kind of houses the system and Google uses it. Then a couple of years later, the 2015 came out. And if you kind of compare this pattern with this pattern and this one, it's exactly the same repeating pattern, the unit cell. It's just that we've gone from a 4 by 4 layout here. This is 8 by 8, and this is 12 by 12, and then this is 16 by 16. So Lockheed and Google upgraded. Los Alamos National Lab, which is where I live, picked up this system here, and then in 2017 the most recent system was introduced, and Google and Los Alamos upgraded. So these are the four product generations that we've been through, and I'll say a little bit about our next generation system at the end. So this is the math slide. There are actually two different ways to think about programming our system. There's this classical optimization problem that we solve, or there's actually this so-called quantum Hamiltonian that describes the wave function of our qubits. And for our first three generations of our system, this is really all that we provided access to for end users. So the way to read this here is we've got qubits. Q sub I means a qubit, so that subscript I might go from 1 to 2048. And so the fact that we've got this AI QI here means that each qubit has a weight on it. And that qubit weight sort of tells the qubit, does it want to become a 0 or a 1? And then we've got, so if that's all we had, that would not be very interesting because the qubits would all be independent, right? And you need coupling between the qubits to have the ability to express complicated optimization problems. That's what comes about from the Bij term. So Bij it corresponds to a physical coupler that allows one qubit to influence a few of its neighbors. Now, because of the engineering difficulty of making each qubit influence all of the other qubits on the chip, we can't have all possible couplings. So in fact, each qubit in our current generation system has coupled or is coupled to 6 of its neighbors, okay? But the bottom line is, this really is the formula that you kind of use as your starting point if you have an optimization problem and you want to map it to our system. So the QIs are the qubits. They're going to be 0 or 1. You get to choose all of the AIs and the Bijs. So with our current system at Los Alamos, there's one A per qubit, so you got 2,000 As. And there's one B for each coupler, so there's 6,000 of those Bs. So literally the instruction, the quantum machine instruction, you can think of it as a vector of these 8,000 numbers, 2,000 As and 6,000 Bs, and that vector of 8,000 numbers defines that landscape that we're going to go look for the minimum of. So easy peasy, right? Everybody can do this. Well, the problem is the idea of taking an optimization problem and mapping it into these sets of A's and B's, that's not a well-known art. A lot of people know how to take optimization problems and turn them into linear programming problems with constraints, but these quadratic models are unfamiliar to the community as a whole. So one of the things that we have to do when we teach people how to use our system is how do you take an optimization problem like graph coloring or traveling salesman, how do you convert that into this form? And it turns out that it's not actually terrifically hard, it's just an unfamiliar set of steps. I mean, I would guarantee that calculus and differential equations is harder than these steps. It's just that nobody actually kind of goes through this math because there's no particular point in it, maybe up until now. And I will point out that this equation up here, this is our quantum Hamiltonian, and we've actually given people access to it now on our 4th generation system. I'm not going to talk about it in too much detail other than to say these AIs are exactly the same as these guys here, and these BIJs are the same as these guys here, but now the QIs have turned into these sigma Zs, and the QI QJ turns into the product of 2 sigma Zs, and now we've got this sigma X over here. So these sigmas are actually, if you remember, the very bottom of the very first slide that I showed you with Feynman on it, at the bottom of that slide there was a set of little matrices. Those are the sigma matrices, and that's what turns that top equation into a quantum equation, because that's not actually an equation between numbers, that's an equation between operators. So on both sides of that equal sign up there, there's really an operator or a matrix which is 2 to the n by 2 to the n, where n is 2048. So that's a great big operator equation up there, and it's kind of hard to think about, but for certain kinds of applications, that's actually a better starting point than the classical optimization problem down there. So as a user, you can kind of attack the system from either one of these perspectives. If you look at the applications that our users kind of map onto the system, it's actually, so last week I was in Milan. We had a European user group meeting, and it was really kind of amazing. A whole bunch of people stood up and talked about, here's what I put on the system. We've kind of developed a catalog of applications. There are about 150 different, I wouldn't call them full-blown applications, but they're sort of like little proto-applications that different users have put on the system. And you can kind of divide them up into 3 main categories. There are optimization problems, which I've talked about, machine learning problems, and material simulation problems. Optimization problems are things like, NASA has done a bunch of scheduling applications. Volkswagen did a traffic flow optimization problem. A company from Japan by the name of Recruit actually converted the real-time auction that happens when companies bid to place ads in your browser. They converted that into a QUBO, and they solved it, and they actually get better results than they do with their standard greedy method. So this is kind of just a smattering of the optimization problems that we solve. Machine learning. Google did some work in collaboration with dWave several years ago called QBoost, and that was the thing that actually got them motivated to buy our system in the first place. Where I am, Los Alamos, there's been some machine learning work as well. And then this rightmost column over here, this is kind of the newest stuff. And this actually fits very closely with Feynman's original vision. Feynman's vision was, if we want to take a quantum system and simulate it, maybe our simulation platform should be quantum itself. So that's kind of what this last column refers to. These are quantum models that we want to understand the behavior of, and we actually map them onto our chip, and we can kind of do this in a very effective way now. So these are kind of the 3 different broad application areas. I wanted to actually showcase something that hopefully brought me a little bit closer to the topic that you guys care about. So this is a piece of work that came out a few years ago from France, and it's actually the multiple query optimization problem. If I have a bunch of queries that I'm executing in a batch, and I have different plans available for each one of the queries, the optimization problem is to make the best choice of plan for each one of the queries, understanding the fact that I might be able to share intermediate results between those plans. And so these 2 authors, Trummer and Koch, converted this problem into one of those binary quadratic optimization problems. And what you see over here on the right side of the slide is the dWave results compared to 5 other approaches. So the dWave is the QA, these red lines. There's the linear approach. This is using a standard linear solver. GA is genetic algorithm. Climb is hill climbing. I'm not quite sure what QUB is here. But the bottom line is the cost is the vertical axis here. So lower is better. We're trying to minimize the execution cost of executing this batch of queries. And then the horizontal axis is how long you've spent in your computation to figure out what's the best plan. And it turns out that the characteristic you see here, it's kind of hard to see it because it's small, but dWave is this red line across the bottom here. So one of the interesting things about our system is we get very good answers very quickly, but we will never produce a certificate of optimality for you. If you solve a linear programming problem on Cplex or Gurobi, they will produce a certificate of optimality that says this is the optimal answer. Because our system is kind of governed by quantum mechanical laws, which are probabilistic, and there's no guarantee with quantum mechanics, we will never be able to do that unless we wrap some classical post-processing around our system. But as you can see here, we're getting very good answers, right out of the chute. And so this is kind of, it indicates the promise that kind of exists with this technology. So a couple of slides here, and then I'll close. Cloud is big, right? So we need to put a quantum computer in the cloud because not everybody is going to want to have one of these things in their backyard. So you can go to https://cloud.dwavesys.com and sign up and get a free account. And we will give away, I think, a free minute, which doesn't sound like a lot. However, one annealing cycle by default is 20 microseconds. So that means 50,000 annealing cycles per second times 60 seconds in a minute is 3 million, I think. So you can do a lot of anneals in 1 minute, and it's just enough to kind of get started. But if you also volunteer to put any code that you develop up on GitHub in an open source kind of way, then we'll renew that minute every month. And again, I'll quote a guy from Los Alamos. He said there's a fairly significant expenditure of intellectual capital required to use up a minute of time on this machine. So a minute does go a long way. So if you guys are curious, I'd encourage you to check it out. And then I'll close with kind of a silly slide here. I wanted to try to say something relevant, and this is as close as I could come. The problem that we face, assuming that this is interesting looking to you and you would like to play with it, the real challenge is, there's a tremendous gap between the world of applications and this quadratic, unconstrained binary optimization function that we minimize. And so clearly, we're in this position where we need to reach out to people, organizations, institutes, to get them to make the investment to come up to speed on this, this thought process and start figuring out how to map problems to this architecture. That paper I showed you about multiple query optimization, we had no idea that those guys were doing it. It just kind of came out of the blue. But clearly without things like that happening, this technology, it doesn't thrive. So the challenge on us is to kind of figure out how to create bridges across this chasm and how to make it easier for people to approach our system, share examples with them, create a community so that people actually see the promise here. I will actually say just a couple of things about our next generation system, which will probably be announced in 2020. So what I'm saying is not an announcement. But the next generation system is targeted to have between 5,000 and 6,000 qubits. The topology of connectivity among those qubits will be radically different. We've gotten feedback from our customers that much denser connectivity among the qubits would be a big win. So the number 6, which is how many neighbors each qubit talks to, we're going to boost that number 6 up to 15. So that's a factor of 2.5. The noise characteristics of our system, we're working very hard to decrease the noise substantially. And yeah, I guess that's pretty much it. Okay, well, I think 15 seconds to go. I'll stop.